Hi, I'm Keenan Casey for Tuts Plus. In this lesson, we'll consider the a priori association algorithm. A priori association is an algorithm that allows us to find frequent item sets within a large data set of, say, transactions. We can also find relationships between specific items within those item sets in the form of if-then rules. I'll explain how this algorithm works. We'll also consider an improvement to a priori, an algorithm called FP growth. Recall that this is the overview of an association algorithm. We take this set of transactions, put them through the algorithm, and we'll get out a set of items that are frequently occurring together. These are the terms that we'll be using in this lesson. First, the item set, which is simply a collection of items. We're going to see that as I. As an example, Chrome loves Star Wars and loves bacon is a set of items from our geek data set. We will define a quantity called support. The support of an item set is simply the fraction, the percentage of the transactions that have that particular item set. We might say in this case the support of the set Chrome, loves bacon is 0.9, meaning 90% of the transactions have those two items. Next we'll define rules, a rule that takes this form, some if-then pair. This is called an antecedent, this is called a consequent. As an example from the geek data set, we might discover that if a person loves Star Wars, then they've read all 4 Lord of the Rings books and they play Magic the Gathering. Lastly, we define a value called confidence, where we compute the confidence of a rule. The confidence of a rule is simply the support for the antecedent and the consequent divided by the support of the consequent, connecting back to this definition of rules. So for example, the confidence of playing Magic implies that you've read all 4 Lord of the Rings books may be 0.8, according to this formula. There are 2 goals of association analysis. The first is to find frequent item sets. This means items that occur often together. Here are 2 examples from this data set on the right. We found that Chrome and bacon occur together often within this set of data. This is another example involving Lord of the Rings, playing Magic, and Star Wars. The second thing we'd like to find are association rules, and these are built from the frequent item sets. We'd like to see, is there this correlation between playing Magic, say, and reading all 4 Lord of the Rings books? Not only do they happen a lot together, but this thing implies this thing. The main problem with this approach is there are just so many item sets. And let me give you an example of that. If we have a simple set of items, A, B, and C, how many possible candidate item sets are there? Well, if you break that out and make all the combinations from the empty set to the 1 item sets, to the 2 item sets, to the 3 item sets, you'll see that we have altogether 8 item sets. What happens if we add just 1 more item to our initial data set? What are the possible item sets for these 4 items? Well, once again, start at the top with the empty set. We have all of the single item sets, then the double item sets, all those combinations, then the triple item sets, and finally the quadruple item set, all 4 together. If we add up all these candidate item sets, how many do we have? Well, we'll see that we have 16 total item sets in this case. Do you see the problem? By adding simply 1 more element to our initial set, we've doubled the size of the candidate item sets. It turns out that in this case, the number of candidate item sets is 2 to the d, where d is the number of things in this initial item set. This means there are way too many candidate item sets if we have any significant number of items. What's the solution to this? Well, one approach is to reduce the number of candidate item sets, and the a priori principle gives us some insight into a smart way of doing that. The a priori principle says if an item set is frequent, then all its subsets must also be frequent. Now that doesn't really help us state it in that form, but if we reverse it and kind of turn it inside out, we'll see that if an item set is infrequent, then all its supersets must also be infrequent. What does that mean for us? It means we can eliminate a lot of options once we figure out that an item set is not that frequent. For example, let's consider that the item D does not happen very much. It doesn't happen enough for us to consider it frequent. Well, in that case, that gets rid of D, but it also gets rid of any other item sets that D is in. So by simply doing this, we've turned 16 sets that we need to check into 8 sets. So this is the beauty of the a priori principle, is that we're taking this huge quantity and reducing it to a number that's much more manageable. The first thing that we're searching for in a data set using a priori association is frequent item sets. What sets of items happen a lot together. It shouldn't surprise you that this has been performed a lot on shopping data, probably on you if you're a member of any kind of shopping club at a grocery store or even on Amazon.com. Let's consider how this algorithm works. First part is, how do we create item sets that are frequent? To do so, we'll start by setting some minimum support level. This might be 80%, it could be 90%. We can set it however we wish. We will not consider item sets that are less than that level of support. We'll initialize k to 1, and k represents the length of item sets that we're considering. We will generate all of the candidate item sets of length k, which is 1 initially. We'll then save the item sets that are frequent, and we're defining frequent to mean their support is greater than our minimum support. Fourthly, we'll generate candidate item sets of length k plus 1, so that'll be 2, 3, 4, and so on and so forth, but we'll do so by only combining the item sets that have made the cut, the ones that we've already identified as frequent because they have a sufficient support level. We'll then repeat this process until no new frequent item sets are found, either through having minimum support or we've used up all the options. So the result of this a priori association analysis will be a set of item sets that occur frequently. The second result of the a priori algorithm is the association rule, this if-then correlation. We'll use the frequent item sets to determine if one item set implies another. The algorithm for doing this is similar, but in this case we are going to use confidence, where we set the value for the confidence ahead of time. Our input to this algorithm will be the frequent item sets that we found using the first step of a priori. Those might look like these on the right. To find the association rules, we'll start with some minimum confidence. This is the minimum confidence that we require in order for a rule to be saved. We will initialize k to 2 and generate the candidate rules from the frequent item sets. And these will be the simplest rules where we have one antecedent and one consequent. We will then save any rules that have a high confidence. And recall that means that our confidence for a particular rule is greater than the minimum confidence that we set. We'll then generate more candidate rule sets based on the rule sets that we found that are a minimum confidence. We will then repeat this process until there are no new rules that can be created. And the output of this algorithm will be a set of rules. Plays Magic implies that you've read all 4 Lord of the Rings books, or if you use so far, that implies you don't play Magic. These are examples of rules that might be determined based on these frequent item sets. The problem with this algorithm is that it's slow. There are so many possible candidates that we have to spend a lot of time checking. We have to spend a huge amount of time creating all these combinations, testing them, and then testing them again to see if they're possibly rules. One solution that's been proposed to this is another algorithm called FP growth. FP stands for frequent pattern. Essentially, what this algorithm does is it stores the data that's important to a priori in a very compact data structure, an FP tree that looks something like this tree shown here, sort of like linked lists combined with trees. And this data structure allows the item sets to be found in 2 passes of the data. In contrast, a priori scans the data set for every potential frequent item set. So this actually in practice may be as good as 2 orders of magnitude better. The a priori association algorithm is a really neat algorithm to find frequent item sets and association rules. It's easy to implement, relatively speaking, and it gives us these 2 things, the item sets that are frequent and association rules that meet some confidence. The weaknesses here are we have to choose the support and confidence values, and secondly, it's very slow on large data sets. In this lesson, we've looked at the a priori association algorithm. It's a type of unsupervised learning. I'm Keenan Casey for TETS Plus. Thank you for watching.